Hello everyone. My name is Emanuel Cambraia. I'm from Federal University of Paraná, Brazil. And this work is called The Influence of Local Dynamics in the Phase Synchronization of a Hindmarsh-Rose Neurons. Thank you for the accept of this conference. I'm very excited to this virtual oral presentation, and it will be my first virtual oral presentation in English. So this is the summary of what we will show in this talk. For the first thing, we're gonna show the individual dynamics of a Hindmarsh-Rose neural model, the maximum Lyapunov exponent, and the solutions of this system. We'll talk about networks and coupling. We'll talk about the phase synchronization Kuramoto, the parameter, to show the results and conclusions. So this is the individual dynamics of the neuron model. This is a system of differential equations with 3 differential equations, and we set the parameters on the right side of this transparency. And B for B and I following these intervals. So if we, this is the maximum Lyapunov exponent of Hindmarsh-Rose model. The final time for this simulation is 20,000 seconds, and this figure represents the maximum Lyapunov exponent. So the black points is a periodic situation, and the colored is a chaotic situation. This figure have 1,000 per 1,000 points, and we set 4 regions on this situation. The first region is a burst regime for a constant number D spike per burst. The second region is a spike regime. The third region is a chaotic burst regime. And the fourth region is a periodic burst regime, like the first region. And the second region, the spike regime, is periodic too. So this is solution for the Hindmarsh-Rose model for individual dynamics. Solutions for X, Y, and Z. The parameters I and B set in this simulation for the solution of the differential equations, systems of differential equations, are here above. So this is for the first region. You can see the same spike per burst. This is the second region, is a spike regime. Again, I and B are set above. And the next one is the solution for the model for a third region, is a chaotic region. Set the I and B here, and you can see is a different spike per burst of the ones of the first burst, of the second burst, of the third burst. Okay, and this is the last one region. The fourth region is same spike per burst and a periodic region. Okay, until now we show the individual dynamics of a Hindmarsh-Rose neuron. Now we will show the dynamics of coupled Hindmarsh-Rose neurons. So the coupled dynamics, it's like the equation 6, 8, and 9. We additioning the current term of the additional current, okay, is like the 7 equation. And you can see the index I on these variables. And the current additional term is like the 7 equation, where epsilon is the coupling, n bar is the mean number of connections of each neurons, and aij is the element of matrix of coupling. So for a network coupling, we in this work used two schemas of coupling of networks: global connections and small world connections. So the global one is everyone with everyone. The small world coupling, and the global and the small world, for this work, we used 1,000 neurons. Okay, for the small world coupling, we used 1,000 neurons too, and a small world scheme generated with a Watt-Strogatz root. So the parameters are 12 connections for each neurons with your neighbors. Each local connections is exchanged by a non-local connections ones with a probability 0.1. Okay. The phase synchronization and the Kuramoto order parameter are shown in this transparency. The phase synchronization is obtained like the standard type, the standard model, but is written on the code like this. How we obtain the phase synchronization? We set the begin and the end of the burst, and we pass the phase around the burst. Okay, so the 13 equation is the Kuramoto order parameter. And the 14 equation is the mean Kuramoto order parameter. And we will use the mean Kuramoto order parameter very much in this work. Okay, we have the third Lyapunov exponent. Lambda 3 is sufficiently negative and that it manages to synchronize periodic or weak chaos before lattice coupling diffuses the neuron behavior. The mean Kuramoto order parameter for a small world coupling is shown in this figure for the 4 regions. So the first region, you can see a non-monotonic synchronization. Start synchronized, lose synchronization, and when we increase the coupling, the synchronization turn again. Okay, the first region and the fourth region, it's like the same thing, but you can see when the region synchronized. The fourth region is so much easy to synchronize than the first region. Okay, the third region is a chaotic regime. So, is a monotonic synchronization. Is a monotonic synchronization. And the second region, a spike regime, it's like a almost monotonic synchronization. Is periodic, is the periodic regime in the spike regime, but the infinitesimal coupling destroys the dynamics and is a almost monotonic synchronization. Okay. The next figure is the mean Kuramoto order parameter again, but for a global coupling. You can see the same things for the region 1, for the region 4, for the region 3, And for the region 2, it's non-monotonic for a periodic regime, is a monotonic for a chaotic regime, is a almost monotonic for a spike periodic regime. So, this is space of parameter for a mean Kuramoto order parameter again. But in this figure, have 90 points per 90, and we can see the same thing. The periodic ones start synchronized, lose synchronization, start synchronized, lose synchronization, and turn back to synchronized again. This is for the small world scheme. We can see the same thing for a global scheme. Start synchronized, lose synchronization, and turn back to synchronized again. These parameters are shown in up of the figure. Okay, and we can found for this model, if we used more points in this figure and do the forward and the backward for any point, some points, this is for third region. We can see hysteresis, but only in a global coupling. The black curve is forward or increasing, and the red one is the lowering or backward. So we have these conclusions. The individual dynamics is the fundamental player in a phase synchronization in the Hindmarsh-Rose neural model in small world coupling regime. Independent of regime, spike or burst, there is synchronization even for extremely weak coupling due to the stability of the orbit of the isolated Hindmarsh-Rose system. We found hysteresis only in a global scheme. So this is my work. Thank you very much. And have my email if you have any question. Please send it to me. Thank you very much. Bye-bye.